Welcome to the very last lesson in kitchen table electronics, lesson 6, tips for lab rats. This is not any formal part of an electronics class, but rather my chance just to throw together some hints and tips based on many years of building electronics for lab applications. And so I'm going to run through some topics here. The first thing I'm going to talk about is data acquisition systems. The next topic will be fast measurement, i.e. measuring pulses with very fast rise times, very high frequencies, or very short pulse widths. Low noise measurement, meaning very small signals. And then finally, I'm going to suggest a project to you that if you are mad keen on electronics and want to continue, I would have built into a longer class. I think if you've gotten through to this point in the class, you agree there's already been enough material. So let's begin with topic 1, which is data acquisition systems. As you well know, your $11 Arduino is slow and doesn't really give an analog output. There is this pulse modulation that lets you set a DC level, but it certainly doesn't let you generate some arbitrary waveform. So what are the things you need to think about when you are looking for a data acquisition system for your lab? Well, one of them is the resolution in bits. In other words, if you have a signal that will cover some voltage range, and you know the smallest change you want to detect in that range, that will tell you then that if you manage to match the entire voltage range to your detector system, which by the way takes a bit of thought, it'll let you know how many bits you'll want your conversion system to convert into in order that you have at least a bit or so a change for the smallest change you need to detect. The next thing is the time between samples, either input, in other words, with what frequency is the input voltage sampled, because that then through the Nyquist theorem will give you the absolutely highest frequency you can detect. And then for outputs, the time interval between the writing of outputs. And if you're lucky, you'll get a chip that actually will do a digital to analog conversion rather than pulse width modulation. We'll talk a little bit about how to do that. Here are some alternatives that I've found. I don't know by any means that this is exhaustive, but anyway, I'm going to use these as examples of what you can get. The absolute standard here is the National Instruments Data Acquisition System with LabVIEW programming. As we'll see on the next slide, it's expensive, but LabVIEW and National Instruments have developed pretty much a stranglehold monopoly on this market, and so the result is you will probably have LabVIEW cards available in your lab, a LabVIEW license, and so on. And so there really isn't a reason to go someplace else. However, if you're starting a lab from scratch, you might well want to look at the alternative. There's a very interesting series of semi-open source microprocessors called Teensies that are a direct spin-off of the Arduino, but with much higher performance, and a very nice website that gives you information on code and so on. It's almost like an open source program for data acquisition for labs. And then there's a very interesting one that I have bought but haven't had time to play with yet, so I really have no idea as to whether it meets the promised performance, but it's called the Red Pitaya, and it looks absolutely sensational, and it's been a favorite amongst radio hams for building software-defined radios. Generally speaking, none of these systems will sample signals at much more than megahertz. Sometimes kilohertz, and as you see with the Arduino, it's even lower than that. At megahertz sampling ranges, something else you have to think about is you have to shuttle the data from your data acquisition system into some program in the computer that's going to display and analyze your data. And if you really do acquire data at very high rates, then passing it to the computer can become quite tricky. And then you're faced with the problem quite often of having to spool through a vast amount of data at a later time looking for signal events. So just because you can go quickly doesn't mean you can use the data. Finally, I'll mention that if you need to look at fast events and your source of signal is repetitive, you are in luck, because there are many, even quite cheap, digital sampling scopes that rely on repetitive sampling of a waveform, so the sampling can occur at pretty low frequency, but by staggering the time intervals of sampling to very short intervals, you can plot out waveforms that are changing very rapidly. So here is a table. You'll have a printout of this presentation so you can look at it at your leisure. So the top two entries here are National Instruments, and the low-end cards have a resolution of 12 bits. Once again, you've got to decide whether 1 part and 2 to the 12 is adequate for what you need. The time interval of sampling is 50 microseconds, which is a long time. 100 microseconds is 1/10 of a millisecond, or 10 kilohertz. So these things are down around the 10 kilohertz range. Remember, the Nyquist theorem brings you in a factor of 2. There is an analog output which puts out on a similar time scale, so once again about 10 kilohertz. These boards have 8 channels. You better check that the channels do not rely on multiplexing, because if they're multiplexing and you're using all 8 channels, you could be down from 10 kilohertz to around 1. The cost of these boards is about $400. National Instruments go up to high-end boards, and here's an example of one of them, 16-bit resolution, 1 microsecond, so you therefore could look at 500 kilohertz, both in and out, which is nice, also 8 channels, but you're paying $10,000 for the board, so beware. But once again, if your lab already has a license, LabVIEW is a industry standard visual programming environment in which you move components around in a GUI to set up your program. Some people love it, some people hate it, but the chances are there is a LabVIEW programmer near you. As you know, my prejudice is the lovely Python. So let's go on to Python-driven systems. You've just seen the Arduino and Pythomata. Here's the Teensy. So it's actually quite impressive because it is based on an Arduino board, but you see 16-bit resolution like a high-end National Instruments. It's only just a little slower in digitization, so perhaps sort of 300 kilohertz as opposed to 500 kilohertz. The analog output is slow though, 25 microseconds, so it's more like the National Instruments low-end boards where one's talking about 10 kilohertz or so for time variation. As you know from our experience with the Arduino though, that's a huge improvement on the Arduino. It has 16 channels with 1 analog output, and here's the great bit, it sells for $30. So I think there's a huge inducement here to get one of these and just play with it. I have a colleague who instruments his lab with them and he loves them. So then there's this red Pitaya. It's more expensive, it's $300, but it has 125 megahertz sampling rate. So this will work well up into radio frequencies. As you can see here, this is actually on the order of 20 nanoseconds sampling in and out. So one is looking at sampling waveforms and generating them on the 50 megahertz timescale, which is kind of amazing. 14 bits is standard and 2 channels. I'll just mention one last thing, which is most of these chips are capable of pulse width modulation output on a digital channel, And there are much faster ways of converting pulse width modulation than the way we used in this class. Here's an example of a chip, the LTC2644, which will do that pulse width to analog conversion quite rapidly. Okay, let's go on to handling fast signals. So we've worked with very low frequency signals, and we've had breadboards connected together by jumper wires, and things worked fine because we were at low frequency. However, as soon as you start getting up into high frequency, the extra capacitance and inductance introduced by wire leads becomes significant. How significant? Well, to give you an example, a frequency of 150 megahertz, and so you can think of that in the time domain as 1 over 150 microseconds, so a few nanoseconds. A frequency of 150 megahertz has a wavelength of 2 meters. So a quarter wavelength, which is 25 centimeters, would make an absolutely, or 50 centimeters rather, would make an absolutely fabulous antenna and radiate away all your energy. So how do you communicate fast signals, either a high frequency sine wave or a pulse with a very narrow width or a very sharp rise time, which by the Fourier theorem we dealt with in the last class means high frequency components? The key is to use a transmission line. Hopefully you've had an E&M class and covered transmission lines, but these are circuits that act like lumped L&C continuously distributed, so that these things are like filters with a passband over a broad range of frequencies. They have a cutoff frequency that you can find on the specification for the transmission line. Usually you will use a coaxial cable. I'm sure you've seen coaxial cables around the lab and around your TV set, but this is what they look like. They have an inner conducting core, a dielectric layer around it, an outer metallic shield, and then a plastic jacket. They're often used for very low frequencies for the very good reason that you can ground the shield and then have a Faraday cage for your low current signal, for example. Although, be warned, and we're going to come on to this topic, if you pass a very low amplitude, low current signal through this, so very small currents, the capacitance will kill you, and we'll talk about that later on. But anyway, the characteristic impedance of a coaxial cable used as a transmission line, i.e. for high frequencies or fast pulses, in its passband of frequencies, because they do have an upper cutoff frequency, is given by this formula. Z in ohms is the square root of the inductance per unit length divided by the capacitance per unit length. You'll remember from the formulae for capacitive and inductive reactance that they each have an I in them, the minus I in one case and a plus I in the other. So this has a minus times an I times an I, which then is just 1. So this is real, and the value of the reactance of the cable then is real and just usually 50 ohms, and I'll explain why in a minute. The reactance of a general cable is given by this formula here, where this is the logarithm of the ratio of the large diameter to the small diameter of the two conductors, and usually this is made to be either 50 ohms or 75 ohms. The reason is that dipoles that radiate effectively have an intrinsic resistance from electromagnetic theory of about 75 ohms, and so a 50 or 75 ohm cable is pretty effective for power transfer into a radiating dipole. Remember the little theorem we proved that when source impedance matches load impedance, maximum transfer occurs. Most coaxial cables have a capacitance of around 25 picofarads a foot. A very big cable might have less. So this 50 ohm cable we were talking about, using the formula on the other page, would have an inductance of around 60 nanohenries per foot, and then if you take the ratio of those and the square root, you'll end up with 50 ohms. Now, if you just take a piece of coaxial cable and hang it on your circuit, if it doesn't go anywhere, like for example a radiating dipole, it's just going to look like a capacitor, and so it's going to slow your circuit down. So here's a formula that once again comes from electromagnetic theory that says that if your cable has an intrinsic impedance or reactance ZS, and the load on the end of the cable, which could be a resistor, remember the reactance of a transmission line is resistive, is ZL, then the amount of amplitude reflected back if you have a wave in the cable and a load ZL at the end of the cable is given by this formula here, ZL minus CS over ZL plus CS. So consistent with what we were talking about source and load impedances matching each other, if ZL equals ZS, the reflection coefficient is 0 and all the power in the cable is transmitted to the load without any of it being reflected back. Why am I telling you all this? Well, it's important if you want to measure fast pulses or very high frequencies or very narrow pulses. You can't use your oscilloscope as it is. Why? Because your oscilloscope typically has an input impedance of 1 megaohm. So if you just plug a coaxial cable into your oscilloscope, you have an unmatched load to your 50 ohm coaxial cable. And so in order to solve this, what you have to do, and I'll show you a picture in a minute, is short out the input of your oscilloscope with a 50 ohm resistor. And yes, this means that you will introduce a reduction of your signal amplitude because of any Thevenin resistance at the source at the other end of the cable, but this is what you're going to have to do to see fast signals. So let's look at an experiment here. Here is an oscilloscope connected to a square wave generator, but via a long coil of unterminated coaxial cable. So you can sort of see the underlying square wave here, but you'll notice it's got this funny shoulder and blip on it here. What is this? This is the previous square wave being reflected from the unterminated end of the cable, and this time delay here on this little shoulder is actually equal to the length of the cable divided by the speed of light times something called a velocity factor. So when you look up your cable, you'll see it'll have a velocity factor of 0.6 or something. That will depend on the dielectric in the cable, and that means a pulse will propagate down that cable with 0.6 times the speed of light, and so you can work out the propagation delay in the cable. It doesn't matter if your scope is properly terminated, but if it isn't, you will see pulses reflected back with twice that delay time if they have to go down the cable and back again. Here's a picture of a terminator. It's actually a homemade terminator. You can buy terminators for BNC connectors. And by the way, I don't know if I've said this in an earlier lecture, that these connectors are actually designed to be 50 ohm impedance to match 50 ohm coaxial cable, and they have a very nice little clipping system on them, and they were invented by the Royal Navy in World War II, which is why they are called British Naval connectors. And so here is your incoming coax, here is a T-piece onto the oscilloscope, and then on the other side of the T-piece, shorting to ground, you see these resistors soldered to the outside of this barrel here, is a load of 50 ohms with those resistors in parallel. Finally, I want to say something about laying out high-frequency circuits. They look quite different from the crow's nest of nasty random wires that we've used throughout this course, and that is because you want to minimize inductance and capacitances between component elements. Specifically, if you have to send a signal through these boards, you will use a pair of printed circuit board tracks as a transmission line. And if you think that's exotic, that's exactly what happens around your computer chip, which actually these days will have a clock in the gigahertz region. And these things just wouldn't work if you tried to propagate the signals through ordinary printed circuit traces. So transmission lines are fabricated on the board. This particular circuit has chokes that are actually printed inductors. These are multiple loops here. It also has here a resonant transformer. This loop is made to be a resonant circuit at the frequency that this amplifier works at, and it's a transformer coupling this circuit to this circuit here. Notice the surface mount very small capacitors. This is so that the lead of the capacitors is minimized. In this course we've used old-fashioned radial wire lead components so that we could plug them into our breadboard. At high frequencies these would be radiators and couple horribly to other leads via stray capacitance. So one wants very small capacitors soldered directly onto the board, and most components these days are surface mount. So all the power supplies come in with a surface mount capacitor to ground. Finally, this board here, you see the dark part all around here, is actually a ground plane, and so this is a region at zero potential, and it just helps to minimize capacitance and inductance on the board. Alright, we're now going to turn to the final topic in this Hints for Lab Rats, and this is low amplitude signals. So this here is a schematic for a current to voltage converter. So for example, I used to build scanning tunneling microscopes, and they looked like a current source here. Anyway, anything that's a current source, which could be, for example, a photo detector, which will generate a current when light hits it, generates some number of picoamps, which is a number of picocoulombs per second going into this terminal here. Well, you'll know that in order for this op-amp to work, you want to take exactly that amount of current out of here, so the net current into the operational amplifier is zero. This is done by having the output go to minus I in divided by R, where R is this feedback resistor. And if you want to generate a significant current, for example from 1 nanoamp, 100 mega ohms from Ohm's law, and this formula here will generate a current of minus 0.1 volts. So this then is a low current amplifier, and it looks very pretty like this, but we have to be careful. Since the currents are very small, any resistance, like a fingerprint on the circuit board, can generate leakage current into these inputs, and stray capacitance really matters. So if you've got any source of an oscillating field around here, and the capacitance is even a picofarad or so, and a picofarad's a very tiny capacitor, so you can have two wires that are parallel to one another and even a centimeter apart or so, and they can generate picofarad capacitances. So there are picofarad capacitances all over this thing, connecting this op-amp to other places. Now you might think, well, this isn't high frequency, why is he worried? Well, I tell you why I'm worried. Circuits in the lab generate a lot of 120 Hz noise. Actually, very nonlinear devices like fluorescent lights actually generate noise all the way up into the tens of kilohertz region. But let's take 120 Hz because this is very typically what you would see from an old-fashioned incandescent light bulb. So a 1 picofarad capacitor, check this out, 1 over omega c, at 120 Hz, so 2 pi times 120 Hz for omega, has a reactance of 1.3 gigaohms. Now this sounds like a huge resistance, but look, this feedback resistor here to get us our sensitivity was 100 megaohms, and you might well have wanted to in fact use a gigaohm. So stray capacitance is providing signals into this op-amp that are every bit as big as this feedback circuit, particularly if R was a gigaohm. So that is a big problem. You really want to minimize stray capacitances. So in a funny way, all of the things I've said about high frequency circuits apply it to very low noise circuits. You want to keep leads very short, you want to screen things, you want to minimize stray capacitance. Now the leakage resistance is an issue because it's very hard to avoid gigaohm connections between some track on a printed circuit board and, for example, a 15-volt rail. The way to do this is to make sure that the printed circuit track around the inputs to the op-amp is held at the same potential as at least one of the inputs to the op-amp. And this arrangement, and this is taken from a data sheet for an OPA 129, which is a standard low noise operational amplifier used in current to voltage converters. This is part of the data sheet that shows you how to build a guardrail for a pin device here and for a surface mount device here. So you better read the manufacturer's instructions and make sure your printed circuit board is laid out per the manufacturer's advice with an appropriate guard around the inputs. Once again, the idea is that if the guard ring potential is the same as the potential of the input, then no current can flow between the two and stray capacitance doesn't matter. Even so, pickup from stray electric fields can be very significant, so all the electronics need to be kept in a enclosed conducting enclosure or a Faraday cage. So if you have a continuous conducting medium around your circuit, then you know from elementary electricity and magnetism that the electric field will be completely excluded from the interior of the cage because the exterior will polarize to exclude it. The final thing is a killer of all low noise circuits, and that's something called a ground loop. This is a common track or wire in a circuit that carries both your signal and another signal that, for example, might be a power line. So, for example, the power line, while it might be carrying a low current, might occasionally have a transient on it where the current raises to a very large level. And then if you have a printed circuit trace that, say, has, I don't know, less than 1/10 of an ohm of resistance, but you transiently get an amp of current in it, that would be less than 1/10 of a volt, which if you're measuring a millivolt would absolutely kill you. So this situation is called a ground loop. They're very common, and so you want to keep signal circuitry well isolated from power circuitry. So to summarize some of these points, I'm going to show you a box that I built in my workshop at home, actually for use in my lab. So in this little section here, there fits a chip that has tunnel junctions on it, and it generates currents in the picoamp range. There are actually 4 little circuit boards around this containing an OPA 129. So one of the points is these OPA 129s on these boards here have their power supply decoupling capacitors and their feedback resistor mounted as surface mount devices. So you can see the whole circuit is absolutely tiny. The leads then, unfortunately, there is some stray noise in coupling because in the best of all possible worlds, these chips would be right up against the thing they were trying to detect. But because we're not very good at making our chips, we make 30 junctions on a device and then we use this sort of telephone plug board arrangement here to find the chip that's working. And so unfortunately we are limited to quite a bit of stray capacitance, and that does limit our circuit performance. The whole thing's in a Faraday cage. There's a lid that screws onto this box, and I've scraped the paint off the regions where the screws go in, so the lid is well connected to the box, and when you put the lid on, all the noise goes away. Then finally, there's a trick that I really recommend for labs that would have me fired at an engineering company, and it's this. All of the power for this box comes from batteries. So there are plus and minus 15 volt batteries here. There are a couple of 1.5 volt batteries to generate a bias source for our tunnel junction. The plus and minus 15 volts feed our op amps. This 9-volt battery here feeds a meter that tells you the voltage being applied to the tunnel junctions. And so each circuit element has its own completely isolated battery. So there is no common lead that feeds power anywhere and signal. So signal and power are completely separated. And finally, the signals come out here on these BNC connectors. Okay, so that is a few things about low noise circuits, and I think we've just about covered everything I wanted to in this course. However, you now have yourself a beautiful oscilloscope which you might sell on to the next student, or if you've gotten addicted by the taste of electronics, you might want to hang on to, and you'll surely want a better signal generator than the one we made on our breadboard. But you've already got a pretty good programmable signal generator, and something I had intended to do when I thought of designing this class was actually ending with a construction project, but time being what it is and academic scheduling being what it is, this would be far too much for this 7.5-week online course. So I'm going to leave it to you, if you want to take the next steps. The one thing that needs to be done with our AD9850, apart from putting the whole unit on a decent printed circuit board with the Arduino so you haven't got those wires flying everywhere, so that's a fairly simple layout job, but the weakness of it, if you remember, was it has quite a high internal Thevenin resistance, and we ended up using a 10K load so that we didn't load the AD9850 in any measurable way. Well, as we've just discovered, we'd like to be able to drive 50 ohm loads, and we clearly can't do that with our AD9850. However, op-amps to the rescue. I recommend you do your own search, but here's one I found, the AD8061. I think it costs only about $3. It has a gain bandwidth product of greater than 90 megahertz, which means that its gain has fallen to unity at 90 megahertz. So if you use this as a unity gain buffer amplifier to change your impedance from whatever it is on the AD9850 down to something much less than 50 ohms, which is probably how you'll use it, you'll still have a bandwidth that approaches 90 megahertz. So the other thing about this particular chip is, like an increasing number of chips, it's a single rail power supply. It'll take up to 8 volts. You have a 5-volt supply on your Arduino, and this chip will work with anything above 2.7 volts. So this is perfect for converting the output of the AD9850 to low impedance. So my suggestion for a project is to take the layouts of your AD9850, your Arduino, and lay a board out with headers so you can plug your Arduino into it, plug your AD9850 into it with all the right interconnects as tracks on the board, include on the board your analog devices AD8061 and feed it from the plus 5 volts rail on the Arduino, then put it all in a box. Make a hole in one end for the USB connector of the Arduino to stick through, and then put a BNC connector on the other end for the output. And then you've got yourself a beautiful little signal generator that you can already run with our AD9850.py or test.py program. Actually, if I was doing it, I would go back to practicing my chops on GUIs, and I would make a nice little app that would bring up a window with a rotary dial that would let me select my frequency and some range buttons, and have a digital display of the output frequency. If you wanted to be super duper clever, you could look up programmable attenuator chips. These are chips that will put in steps of decibels attenuation depending on which pins are activated, and you could program them from your Arduino. But I leave that all to you. The point is, you're a few dollars and a few hours of what I hope would be great fun from building a world-class signal generator. With that, if you've made it to this point, congratulations, you're a fully fledged lab rat and ready to go on to use electronics to make great discoveries, and build great things.